Okay, today we're going to do a chi-square goodness of fit test. And if you turn in your notes to this first page, you can see I've got the highlighted, what it's highlighted. That's what I'm going to be talking you through today. We're going to do a goodness of fit test. And the first problem, our null hypothesis, will be similar to this first one that says the observed counts are equally distributed. The assumptions, we're going to make sure we've got a random sample. Our expected counts are all bigger than 5. We're going to find our expected counts by taking the total frequencies and divide it by the number of categories. Degrees of freedom will be categories minus 1. We're going to compute our test statistic by taking the sum of our observed minus expected counts squared over expected. And then we're going to find a p-value by either typing our data into list 1, list 2, and choosing chi-square goodness of fit test, or by using the chi-squared CDF command on our calculator. So let's go ahead and get started. If you want to pause the video to read the problem, you can. Now, reading the problem, basically the idea is this spinner over here, is this a fair spinner? So if we spin the spinner 100 times, do we land on each section the same number of times? Is it equally likely? So down below, someone doesn't think it's fair, so they would spin the spinner 100 times, and they landed on the skunk section 33 times, 121 times, 220 times, and 526 times. Now, that's actually what happens, so those are called my observed counts. Now, you have to come up with the expected counts, so you have to think of the question, if you spin the spinner 100 times, how many times do you expect it to land in the skunk section? And since the spinner appears to be equally likely as far as 4 sections of the same size, the way we would come up with the expected counts is we would take the 100 spins and divide it equally into by 4. So take 100 divided by 4, and from that you get 100 divided by 4 is 25. So each expected count would be 25. We would expect if we would spin the spinner 100 times, we would land on each section 25 times. All right, so knowing that, we're going to go ahead and do our significance test. The first thing you do is you state the null hypothesis. What's different about a chi-square test is our null hypothesis is going to be in terms of a sentence. So basically, our null hypothesis would be that we're assuming the spinner is fair unless we have enough evidence to say otherwise. So your null could be the will is fair, or your null could be the will is equally likely, or you could say the distribution of the outcomes on this spinner are the same or equally likely. Now, the alternative is the opposite. So we want to see if we have evidence to say that the wheel is not fair or not equally likely. All right, so we've got our hypotheses. We write them as a sentence. Again, this is a chi-square goodness of fit test. And we're going to check our assumptions. Now, the first one is still a simple random sample. In this case, we're going to assume it in this context because if you play a game of chance, that usually involves spinners, dice, and those are usually considered to be random. And that's kind of what we're testing. So we're going to assume that we have a simple random sampler because a spinner is really, spinning a spinner is a random event. So we can assume it's a simple random sample unless we have evidence to say it's really not random. The next thing we have to check is our sample size. Is it large enough? So we go back to the expected counts, and our expected counts were all 25. So remember, we listed all the expected counts. Each one was 25, and we take 25 and we make sure it's bigger than the number 5. Now, if every expected count's bigger than the number 5, then we are okay, and that our sample size is large enough, and that assumption is met. All right, now since both assumptions are met, our result should be valid. So we're going to go on to the mechanics. We write down our chi-square test statistic formula, which is the sum of our observed minus expected value squared over expected. And then we're going to go back to the table of data. We had 33 times the spinner landed on skunk. That's observed. We expected it to land 25 on skunk. So we're going to compute 33 minus 25 squared over 25. Now notice we've got a sigma here, meaning we're going to add that, we're going to do that for every category and then add them up, and that's going to be my chi-squared statistic. So we're going to go to the next category of 100. Our observed count's 21, our expected count's 25. So we say observed minus expected squared over expected plus. Then we go to the next one, which is 20 minus 25 squared over 25 plus. And we go to the last one, which is 26 minus 25 squared over 25. And if I put that in the calculator, add that up, that should be my test statistic, which is 4.24. Now, in terms of degrees of freedom, it's the number of categories minus 1. So it's not how many times, it's not 100 minus 1. So it's not how many times you spin the spinner. It's the number of categories. So we have skunk, $100, $200, $500. There are 4 categories. So therefore, the number of degrees of freedom is 4 minus 1, or 3. Now, finally, to get the p-value, I can use my calculator with chi-square GOF. And if you read this down here, here's the instructions to do it, so you can follow along with your notes and review that later. I'm going to show you how to use the calculator now to come up with the chi-squared statistic and the p-value. So to do that, you're going to go to your calculator, and you're going to hit Stat Edit. And in list 1, you're going to type your observed counts. And in list 2, you're going to type your expected counts. So pause the video and type those now. All right, once you have them typed in, you're going to hit Stat. And then we're going to go over to Test. And then we're going to scroll down till we see chi-squared GOF. Now, there's 2 chi-square tests. The one we're doing today is letter D, chi-squared GOF test. So hit Enter. My observed counts are in list 1. My expected counts are in list 2. I have 3 degrees of freedom. Now, if I hit the draw feature, you can see that the chi-square test statistic is actually a distribution that is skewed to the right. Now, it does turn out as n gets really, really big, or the number of categories gets really, really big, degrees of freedom gets large, this distribution does become approximately normal. But when I have just a small number of degrees of freedom, it's going to be strongly skewed right. Now, my p-value is always going to be the right tail, and the right tail, you can see the p-value is 0.2367 underneath the picture. So we're going to come back over here, and we're going to write down the p-value, 0.237 if I round, and you can say about 23% or 24%, the right tail was shaded. Kind of ignore these numbers. These numbers down here will change. If the numbers were accurate, I would put 4.24. So my chi-squared statistic is 4.24. This picture is going to change as the degrees of freedom changes. So does the values on the horizontal axis. But about 23%, 24% of the area should be shaded. It's always the right tail, and where it hits, that's where your chi-squared statistic is 4.24. All right, ready for the conclusion. So we take our p-value, which is 0.237. So we're going to say since our p-value, which is 0.237, is greater than alpha, which if we don't know what it is, we just write alpha being 0.05, we fail to reject the null hypothesis. Now, if we fail to reject the null hypothesis, then you say there is not enough evidence for our alternative hypothesis. But again, we want to make sure we use context, so we don't write that. So we go back. My alternative hypothesis said the wheel is not equally likely. So there's not enough evidence to conclude the wheel is not equally likely. Or you could say there's not enough evidence to conclude the wheel is not fair. All right, now we're going right underneath. We want to determine which value on the spinner contributes the most and the least to the test statistic. So if I go back to the calculator, if I choose to pick instead of the draw feature, if I choose the calculate feature, we're going to hit stat, test, and we're going to go down to chi-squared goodness of fit test, which I down here, I think letter D. There it is. But instead of draw, we're going to hit the calculate feature. And there's our test statistic and p-value degrees of freedom. But right underneath it says contributes or contributions. And you see 2.56, 0.641, 0.04. So what that means, if you go back in our calculations for our contributions, this first contribution, 33 minus 25 squared over 25, if you calculate that, that turns out to be 2.56. And the next ratio is 0.64. And the next one is 1. And the last one is 0.04. So again, on the calculator where it says contributions, the first one's 2.56. And if I compare, that's the biggest contribution. So my first category is going to contribute the most. And the last one, the 0.04 or 0.04 is the smallest contribution. So my last category is going to contribute the least. So if we come over here, if I say which one contributes the most, the one that contributes the most is the first category. And if I say which one contributes the least, that's going to be this last category. Okay. So I'm going to go back and I'm going to say, well, in the context of the problem, which one's the most, which one's the least? So skunk was the first one. So the skunk contributes the most, and $500 was the last one. So 500 contributes the least. Okay. So the most would be the skunk category, and the least would be the $500 category. And that's because if you look at the observed and expected values, on the $500 category, the observed was 26, the expected was 25. So those two values are pretty close. So if I do 26 minus 25 squared over 25, that's going to be smaller, that ratio, than the very first category of the skunk, which the difference between the observed and expected were much larger, 33 and 25. So again, which one contributes the most and the least? We can get that from the calculator where the CNTRB, that's what that stands for the contributions to your test statistic. And you can calculate that, and that's really basically telling you what each ratio adds up to. All right, so the last thing I want to talk about is on the calculator, how else can I get the p-value? So if we go to second vars, and we scroll down to number 8, there is a chi-squared CDF command, and I can get the p-value this way as well. So my lower bound is always going to be that test statistic. So if you go back, our chi-squared test statistic in step 3 of our significance test was 4.24. My upper bound is going to be infinity, something really, really large, and degrees of freedom for this problem. Again, categories -1 was 3. Hit paste. And we can see there's our p-value. That's just another way to come up with the p-value. Okay, that's it for problem 1. Go to the next video for problem 2, and we'll see you then.